Single layer perceptrons. In fact, the next few lectures will be related to single layer perceptrons only. So, in particular, under the broad heading of single layer perceptrons, we are going to discuss about the third methodology for unconstrained optimization, because two of the approaches we already covered, which is the steepest descent approach and also Newton's method. These two we have done, and today we are going to consider the third one, which is based on Gauss-Newton method. Okay. But before we actually begin today's topic in general, there are few more things which I'd like to do. So far you have gone through, I think, 11 or 12 lectures in this whole series, and what I have been trying to tell you is different aspects of neural networks, trying to go through the learning mechanism and then the single layer perceptrons. These things we are telling, okay, and also to the distant viewers, I think all these information is getting available. But what we can't present to the distant viewers is the kind of discussions which I quite often have at the end of the class, because the students are asking questions, but a lot of times at the end of the class there are some interesting sessions that I have with the students, and I thought that sometimes sharing such things with the distant viewers might be of help. Now, one of the things which I'd like to point out, of course, in a lighter mood, is which was pointed out to me last time, that we were discussing sometimes back about the times in which all the different theories of neural networks were discovered, and we were telling about the time of 1990s when we talked about the theories of Vapnik. So, in fact, going by the historical chronology of neural network, I think we should first begin with 1943, okay, when McCulloch and Pitts, okay, I think we have already mentioned their names, McCulloch and Pitts. They first presented the theory of artificial neural network as a computing machine. Okay. So, the basic fact that ANN can act as a computing machine, okay, that was shown by McCulloch and Pitt. Their model presented that. And then we had in the year 1949 the theory by Hebb, okay, which was the first rule on the self-organized learning, okay, unsupervised sort of thing, because you know that Hebb's learning theory, which we have already seen, okay, that is a self-organized learning which is entirely dependent upon the presynaptic and postsynaptic activations. Okay. So, that is the second thing. And then also, most importantly, the one which we are discussing right now is a theory which was proposed in 1958 by Rosenblatt. Okay. In fact, he is the inventor of perceptron. One can surely give the invention of perceptron to the credit of Rosenblatt, but that was in the year 1958. In fact, following Rosenblatt's theory in 1958, okay, in the 60s we had seen a lot of turbulence related to the development of perceptron. Okay, and I use the word turbulence intentionally, because in 1961, okay, it was another scientist, Minsky, okay, he pointed out some of the very fundamental flaws of the perceptron model, which I have already told you is that it can, the basic perceptron model can only classify linearly separable problems. And the example which I had given to you in the last class, that's to say, for a simple 2-input logic gates using the AND, or these things are very easily linearly separable. but a simple problem like exclusive OR, which inherently is not linearly separable, that could not be solved using a perceptron model, which I had shown. Now, Minsky in fact was the first to point out this, that the non-linearly separable classes, okay, they cannot be classified using the perceptron, and that had given a big jolt to the theory of Rosenblatt. And in fact, the growth of neural network, rather the growth of the perceptron as a computational unit, okay, suffered quite a lot till the time the multilayered perceptron theory was presented. Okay. In fact, we will be discussing little more about it when we come to the multilayer perceptron discussion. Okay, but so much for it now. So the theories that we are talking of is basically the early 40s, late 40s, late 50s, that type. Okay. Now, very interestingly, last time we were discussing about Newton's method. Okay, so the question that came to people's mind was that, how is the great scientist Sir Isaac Newton getting associated with neural networks? Something very interesting. In fact, Sir Isaac Newton has in no way contributed to the neural network as such, but his theories are there everywhere. His theories are there in the sense that when we try to use the mathematical model, there we try to use the Newton's theory, okay, based on which we had already presented the analysis. So, although Newton was born in the 18th century and all these theories are 20th century, late 20th century theories, okay, Sir Isaac Newton in fact doesn't have anything to contribute to neural network. Anyway, so we can begin with the Gauss-Newton method, but again before that I thought that we should spend a little bit of time on the differentiation of a function with respect to a vector, because that's what we were discussing in the last class, and I don't know if some students over here or if some of the distant viewers had any problem in getting into the theory of the differentiation, because we were directly using some of the results which I thought that maybe we should spend a little bit of time in order to explain such theories. Okay. So, we will be first talking about some of the theories related to the differentiation with respect to a vector. Okay. Okay. And let us say that we take a real valued function, let us say f of w, but again I take w vector, okay, because there are many free parameters in the system. So, let us take any function real valued. So, this is a real valued function of a parameter vector w. Okay. In fact, let us talk in very general terms. Okay. We know that in our case w vector means the weight vector, okay, but any parameter space, let us say a function of any parameter space which we are calling as f of w. Okay. Now, when we define a derivative of this function with respect to a vector, okay, let us say that this function f we would like to differentiate with respect to a vector. So, dou f dou w, then exactly what we mean by that is that this w, okay, this w vector, that is after all an m dimensional vector, isn't it? So, w we assume to be an m dimensional vector, okay, and whose elements are nothing but w1, w2, etc. up to wm, right. So, by dou f dou w vector, we essentially define another vector, okay, which will be of this form, dou f dou w1, the first element, okay, that is the function differentiated with respect to w1, okay, and then the second element will be dou f dou w2, and like this we will be having m number of elements, but the last elements or last element or the mth element will be dou f dou w m. Okay. And in fact, I mean this being a vector, this whole thing acts as a vector. Okay. So, there is no harm in giving an overall vector notation to this. This should be a transpose of what I have already written. Okay. Now, the thing is that this is the general form of the derivative with respect to a vector. Okay. But now, let us consider one or two very special cases of this function, okay, which we will be results of which we will be requiring, and in fact, we have been already using some of these results. So, let us take a few typical cases of this function. In fact, two typical cases we will take. The first case that I am going to take is that if the function is expressible in the inner product form. Okay. In fact, we require such functions, okay, very often, because when we are considering the neural network, then the function that we are realizing is very much expressible as a as an inner product, isn't it? So, this in fact becomes I mean x transpose w, right. So, this x transpose w, if we write it this way, that is in the inner product form, I mean algebraically, so this is the matrix form of it, matrix vector form of it, and the algebraic form of this is simply the summation of xi wi, where I is equal to, where I is summed up from 1 to m. Okay. Now, if we take the function like this, okay, and if we differentiate this function f expressible in this way with respect to wi, okay, what is it that we are going to get? Simply xi, simply xi. So, now if I ask that what is going to be this vector, that is dou f dou w vector, it is going to be, yes, x vector, because you see, when I differentiate with respect to w1, let us say that I differentiate this whole expression with respect to w1, then f of w here is x1 w1 plus x2 w2 plus so on up to xm wm. Now, when I am differentiating this with respect to w1, then the only non-zero term that remains is x1. Okay. So, the dou f dou w1 is x1, likewise dou f dou w2 is x2, dou f dou wm is xm. So, that is why if I take dou f dou w vector, that itself will mean that it is x vector. Okay. So, this is a very important relation that we need to remember. That is to say, when the function is expressible in x transpose w, okay, in that case the derivative of that function becomes simply the x vector. Okay. So, we will be directly making use of this. I mean, when we come to x transpose w, we will be directly making use of this dou f dou w definition. All right. Okay. So, this is the simplest of all the forms of the function, that is the inner product form. Okay. But we often, I mean, in fact, we have been expressing the functions also in a quadratic form. Okay. So, when we express the function in a quadratic form, okay, let us put a case 2 under it. So, case 2, we are going to represent the function in quadratic form. And for that, what is the representation that we should make? F of w should be w transpose, yes, yes, x into w, but because here we have already used x, okay, there is no harm in using a different notation for that. So, let us say that we use a matrix, let us say R matrix we use. So, we use, let us say, w transpose vector, R matrix and w vector. Okay. And in this case, what we take is that this w vector again is an m by m vector. So, very rightly, if we take it, I mean, if we take it this way, then in the summation formula, this whole thing can be expressed as summation Wi, Rij, Wj, okay, where we sum it up for I is equal to 1 to m and for j is equal to 1 to m. Is it very clear? Just see that this R matrix is post multiplied by W, pre multiplied by W transpose. So, this is what you are going to get. Okay. So, if you just investigate with these expression, okay, you can see that when we have I is equal to j, okay, that means to say that all the terms where I and j become the same. Okay. This in fact is going to have how many such summations? There will be effectively m square number of summations will be there, isn't it? So, here you can see that for I is equal to j, there will be all these squared terms. I mean Wi square, Rii, those type of terms will be there. So, that means to say taking the diagonal elements of the R matrix, okay, whereas all the other terms will be of this nature Wi, Rij, Wj. So, if we take the function in this form, okay, and then if we take its derivative, let us say that we take a derivative with respect to Wi. So, dou f dou Wi now I take. Okay. Can you tell me that what is going to be the expression for that? So, I am just differentiating with respect to one of these w's. I take Wi, I mean I could take W1, W2, anything. So, I take Wi in general. So, what is going to be dou f dou Wi? It is going to be here summation Rij Wi. That is very good. Okay. So, here it will be summation for I is equal to 1 to m Rij W j. Yes, it should be j is equal to 1 to m. So, I should take Rij Wj, okay, and in this case my I can be from 1 to m. Okay. So, like this I will be getting m such expressions. I mean this is dou f dou W1 will be this, dou f dou W2 will be this. So, effectively again when I write this expression in the matrix form, then what do I get? So, when I take dou f dou W vector, in that case what is it going to be? This is simply going to be R matrix times W vector, R times W. So, R dot W, that is going to be R dot W is going to be the dou f dou W. Okay. This is the representation in matrix form. So, we have got two cases. The first case was the inner product form, okay, whereby we got the derivative as simply x. When it is of x transpose W, we simply got the derivative as x, and when it is expressible in the quadratic form like this, okay, then if you are differentiating this function, I mean beginning with this, if you are differentiating, then you get this. Okay. This is very interesting. So, do not feel confused that if I get a function like this and immediately in the next step I simply write the derivative of that as R dot W. Okay. So, it is understood simply. Now, coming to one of the fundamental definitions of matrix, okay, which we will be needing in our discussion very much, that is about the positive definite matrix. Okay. So, this definition we will be requiring. Now, after all, in this case, what is the dimensionality of this R matrix? This R matrix is going to be an m by m matrix, isn't it? So, R is m by m matrix, right. Now, this R this m by m matrix R, okay, is said to be non-negative definite. So, before we go into the definition of positive, we first define what is non-negative. Okay. I mean, this is very rightly understood that, I mean, if we understand what is a non-negative, then we can always define what is a positive by simply, I mean, non-negative means it is greater than or equal to 0. Okay. So, if you eliminate the 0 case, if you do not consider the 0 case, it is the positive case. So, let us first take the non-negative case. So, R is said to be a non-negative definite, okay, if it satisfies this condition, and that condition I am going to write, okay, that is you take R and you pre-multiply it by A transpose and post multiply it by A, and if this is greater than or equal to 0, okay, for any vector A, that you may find in the m dimensional space. So, when I write R m like this, it means to say in m dimensional space. So, you take any vector A in m dimensional space, and if this relation is always satisfied, then we will be telling that this matrix R of dimension m by m, that is a non-negative definite matrix. Followed? Okay. So, what is positive definite then? Positive definite will simply mean that when this inequality sign is the only thing that remains, that means to say it will not be greater than or equal to 0, it will be greater than 0. So, positive definite will mean if it is A transpose R A greater than 0, again, I mean, the condition is that for any vector A in the m dimensional space. Okay. So, that is the definition of positive definite, and now positive definite matrices, they fulfill two interesting properties. Okay. And what are they? So, properties of positive definite matrix, properties of positive definite. Okay. I think some of you must be knowing, because this is normally covered in any elementary matrix theory. Okay. The first property is that all positive definite matrices are non-singular. So, all positive definite matrices are non-singular, that is R inverse exists, right. So, that is the first property, and the second property is that its eigenvalues, that is to say the roots of determinant of R equal to 0, okay, they are all positive, roots of the characteristic equation. So, this is the characteristic equation, determinant R equal to 0, they are all positive. So, these are the two very important properties of positive definite matrix. Okay. In fact, we will be needing these very soon. Okay. So, is there any question related to the theory that we have?
For positive definite matrix,
Yes.
if the vector A is 0,
if the vector A is 0, a null vector, yes.
in that case A transpose R A becomes 0.
Well, what I mean to say is that, I mean, don't take the 0 case. Okay. I mean, any non-zero vector, okay, that is included. I mean, when I take any vector A belonging to m dimensional space, okay, any vector other than the 0 vector. Okay. Yes.
Differentiation with respect to vector.
Differentiation with respect to vector, yes. Case 2. Okay, good.
This was summation I is equal to 1 to m and j equal to 1 to m.
Yes.
Is omega I r I j omega j. So when I is equal to
W I R I J W J. It is not omega. This is W. Yes.
w, sir, in the case I equal to j,
Ah.
when you will differentiate, will you get a 2?
Yes. I was expecting that somebody will point out that. In fact, I mean that 2 anomaly is existing. You know, when the square terms are there, okay, when I have I is equal to 0, you are very correct in your observation that then the terms are Wi square Rij, those terms, okay. And if you differentiate that, then it becomes 2 times Wi, okay. So you are very correct about it. So in fact, I mean in that sense, I mean when I is equal to j, those cases, I mean it's not accounted. I mean for all I not equal to j cases have been accounted over here by yes please. I mean somebody points out something.
All terms will have two Wij, Rj. All terms, because
All terms will have 2. Yes, yes.
all terms will have two, sir.
Yes.
There won't be any anomaly at all. There is a Wi square and there are two Wij, Rj. Yes.
There are yes. I was in fact coming to that. That here 2's we are getting directly. Okay, I mean for the square terms we are getting the 2's directly. I mean for all the diagonal elements of this R matrix. Okay, they are already contributing to 2, and we get only one of the square terms. So there will be totally m such terms coming in. So where this contribution of 2 will be there, but the contribution of 2 will not be there for the terms which are simply of this Rij Wj type. But remember that when you look at the matrix, okay, Rij, Wi and Wj, then effectively there will be 2 terms that will be contributing, okay, because I mean there will be one coming from this side, one coming from this side. So effectively those 2 when added up, so everywhere there will be a uniformity of 2. In fact, I mean we could express this as half of Wt or W also. In that case, I mean it would have been very rightly written as Rw, okay. But this summation of this will always involve 2 terms. So because I mean this is a double summation term going on within the bracket. So this is okay. So I think I mean it's good that you have I mean raised this doubt and also happen to solve this doubt also. So any no, second term is coming. Why? You see that there is a Wi for each of these Wj's. Okay. So you see when you are adding it up, all right, you will get that. You will be getting Wi Rij Wj and you will be getting Wj Rij Wi. Rji, yes. R, yeah. But yeah. Here the symmetric matrix, I mean we will be in fact encountering, I mean whatever R form we are there. I mean the reason why I brought in R over here is that R later on we will be always considering the correlation matrices, okay, which will be inevitably symmetric matrix, okay.
But sir, this is wrong for a generic case.
No, sir. Again, even if it's symmetric, sir, when we are differentiating with respect to I, we are getting Wj Rij, and we are getting when we are differentiating with respect to J, we are getting Wi Rj. They are in different columns, sir, different rows. So again, we are not getting 2, sir. We are not summing these terms, sir. They are in different rows.
Are they in different rows? That's what we.
One is in ith row, one is in jth row.
Yeah.
Sir, this function has no rows and columns. It's a simple.
No, this function has got no rows and columns. That is true. But you see, you are differentiating with respect to Wi. Now you see. I mean one fallacy in this. Ultimately, you are computing this f of W completely, isn't it? Now, when I say that this f of W, what you have computed, you differentiate with respect to W1, then that will involve the terms where W1 is coming this side, and that will also involve the terms where W1 is coming this side, and that is why the factor of 2 is coming.
FW should be half of this, so that R dot
That is accepted. Yes, here this should be 1 by 2 into this. Yeah, I mean if it is written as 1 by 2 into this, because I mean any quadratic form, in fact that is the reason why all quadratic forms we have been writing as half of WT R W, but here just for the sake of simplicity we did not write down this 1 by 2. Yes, I mean if you are writing it as half, you will be getting as R W. If you are writing it as simply WT R W, then you will be getting 2 times this, and this factor of half, and half here, 1 here, or 1 here, 2 here, that is immaterial. Okay. Okay. I mean properties of positive definite, that is what you want. Yeah, right. Okay. So, we now go over to Gauss-Newton method, that is the third approach towards optimization. So, the approach 3, which is the Gauss-Newton method, in fact the title talk of today is on that only. So, in Gauss-Newton method, okay, we are applying this method actually to a cost function that is expressed as a sum of the squares of the error. Okay. Now, I define a cost function as a function of W, of course. Cost function is equal to half of summation I is equal to 1 to n over EI square. In this case, what is EI? EI is nothing but the error of the ith observation. So, we are making an observation in number of times. Now, please I mean do not neglect this definition, please try to understand it very carefully. So, I am making n number of observations. Okay. So, I is the index of my observation. Okay. I is the index of observation, and I have of course I something that can vary between 1 to n. So, that means to say from first observation up to n number of observation, and by writing it as summation I is equal to 1 to n, I have summed up the squared error that I have got over n observation. Okay. And one thing which I stipulate here is that the weight vector W, okay, the weight vector, that is the W vector, is fixed over the entire observation interval. So, this is fixed over the entire observation interval. Now, I wanted to stipulate this thing so that people do not get the kind of notion that with every observation we are changing the weights. We are not. Okay. We are making n observations, and for all the n observations we have kept the weight to be the same. Okay. And then we are calculating the sum of the squared errors over n such observations, and based on the sum of these n squared observation errors, okay, we are going to ultimately find out a new value of W. Based on these n observations, we are going to find out a new value of W or an updated value of W, okay, which we will use after that. So, in order to get a new value of W, what we should do? We should find out the new value of W such that this cost function is minimized. With the new value of W, the cost function should get minimized. So, that is why we have to calculate now the gradient of the cost function at this point. What point? At the point W is equal to Wn, okay, at the end of n observations. All right. So, when we operate around, the point W is equal to Wn, okay, then the error term that we will be having, okay, can be expressed as the updated error, that is I as E as a function of I and W. Okay. That is very clear because the error will vary from observation to observation, and also the error will vary when you change the weights. So, error is also a factor which is very much dependent upon the W vector. So, E prime is the updated error. Okay. that will be nothing but EI, that is to say the error with the n observation, I mean the error EI, okay, the earlier error I mean to say, plus what happens is that at the point w equal to Wn, okay, you are going to find out the derivative of this error with respect to w vector. Okay. So, derivative of EI with respect to w vector, that you are going to compute at the point w is equal to Wn, all right. And then this derivative you are going to multiply with the incremental weight change. Okay. That means to say that w, then the new w that you are going to get, okay, minus the w that you had at the n case, okay, w minus Wn. Okay. This is something that you will be I mean calculating for I is equal to 1 to with every observation you are going to calculate this. Okay. That is the error will be this. So that I mean at the end of n iterations. So when we are having n number of iterations, okay, when we are having n number of observations, not iterations. Okay. So in the matrix notation we can write that E prime, okay, n w, okay, this will be equal to E n, okay, plus okay, I mean plus what that we will be seeing. I mean this is the Jacobian matrix, and how it comes that I will explain very shortly. Okay, w minus Wn. Okay, this is effectively the matrix representation of this equation. So if we call this equation as what is the number that we can give? Okay, we give a number 3 pertaining to today's lecture. Then equation 4 that we are talking of now, okay, that is nothing but the matrix representation of this, in which case actually this error En that we are talking of, this is an error vector, okay, which will be written as E1, E2, etc. up to En. So there are n number of observations, so there are n number of errors individually. So this is En vector is basically the error vector, okay, of course I mean use the transpose notation for that. So I mean this way, I mean if you take this equation, you can independently compute E1, E2, E3, all these things. So like this you calculate all these things, E1, E2 up to En you compute, and then you represent the whole vector by En vector. So that I mean if you are describing this equation 3 with I is equal to 1 to n, the way you can describe in the form of a matrix vector representation is this relation 4. Followed? Any doubts? Yes, please. Yeah, right. Del E1, del W vector. All right. Now, instead of that, I have written a new matrix which is a J matrix, and that is nothing but the del EI only. So I'm coming to this. So when I transform from 3 to 4 and make it in the matrix form, that time this del EI del W is coming out to be the J matrix. And what is this J matrix? Now you try to have a look at it. You see you have E1, right, or E prime 1 you have. E prime 1 when you have, in that case you have it as dou E1 dou W vector. And what is dou E1 dou W vector? There are m elements of such W vectors. Okay. So that means to say that when I have dou E1, let me write it this way, dou E1 dou W vector, okay, that will be nothing but the I mean it will be written as a, I mean I'll write it as a row vector only. So and then make it transpose. So it should be dou E1 dou W1 dou E1 dou W2 up to dou E1 dou Wm. No, this is yes, this is I mean transpose of this, our transpose of this will be the column vector of this.
But we need a row vector here because you multiply with W or Wn in the last equation.
Just a minute, just a minute. I mean this is our dou E1 dou W's definition will be this. Okay. So likewise, when we make the second observation, when we take the second observation, that is E2, that time we will be having dou E2 dou W as simply dou E2 dou W1 dou E2 dou W2 up to dou E2 dou Wm. Okay. Again a transpose of this. So, that means to say that it is m by 1 vector. Okay. So, by taking this transpose I am ensuring that these are m by 1. This is also m by 1. Clear? So, likewise we will be considering dou En dou W vector. Okay. That also will be this. I am not writing down. So, here actually what happens is that when we are considering these transpose, okay, these I mean derivatives, okay, together in this vector form, then combinedly I am going to write down the gradient of the error vector En. Okay, I mean let me complete this. You see that I have already defined this En vector. En vector is what? E1 to En. Now each of these, okay, each of these errors E1, E2 etc. are differentiable with respect to W. Okay. That means to say when I differentiate with respect to W, that time it leads to m dimensional vector. So, what I do is that now I define the gradient matrix. Now, I define a gradient matrix dou En, okay, where this dou En will be nothing but dou E1, I mean del, I mean that is to say the gradient of E1. And what is gradient of E1? Gradient of E1 is nothing but the m dimensional vector of this, okay, this first one, okay. So, this itself will be written as dou E1, I mean del E1, okay, that is the grad of E1, sorry, grad of E1 will be this, okay. Similarly, this term will be nothing but grad of E2, okay, followed, like this, this will be grad of En. Now, so I have to write this grad of the whole En as grad of E1, grad of E2, okay, up to grad of En, okay. And what is it that I have got here? You see each of these, this is a column, this is an m dimensional column, okay, and I am going to have n such rows. So, this is an m by n matrix. This is an m by n matrix. Why? Because each of these terms are having m rows, okay, and there are totally n number of columns over here. So, it is an m by n matrix, and this matrix, okay, that we have got will be described as grad En matrix. Now, if I take the transpose of this matrix, all right, if I take grad En's transpose of that, that is defined as the Jacobian matrix, Jacobian matrix, okay. And so, what is the dimensionality of Jacobian matrix? Jacobian matrix in this case is n by m matrix, okay. And you can now see that here we require n by m matrix. I think that is something what somebody was trying to point out over here. Previous equation.
Not multiple, because you have taken del E by del 1 as column vector.
No, okay, del E by, okay, right. Transpose of that, yes. But here what happens is that in this matrix notation, this Jn is going to be n by m matrix, and W's are all m vectors. So, W minus Wn is also m dimensional vector. So, it becomes, this product becomes n dimensional vector. So, this expression 4 that I have written out over here, that is actually valid for an n dimensional vector over here. Is it clear? Yes, please.
So how can we take the weight vector to be constant over the whole interval?
That means to say that I make the first observation I is equal to 1, and I do not change the weight of that. Okay, I keep the weight constant at W. Okay, so I make n number of observation, I sum up all the squared errors, that is making a summation of EI square, and then only I am changing the weight. Okay, that means to say that I am minimizing the sum of squares, followed, sum of squares of the observation. Okay. So, now having defined this E vector, En vector, all right. So, in fact, this is what we are back again to. So, I have defined what this matrix is. So, this matrix, J matrix, is called as Jacobian matrix, yes. So, this is the Jacobian matrix. So, Jacobian matrix will be of n by m dimension, where basically you are considering here the m dimensional input you are considering, that is to say the error that you are considering to be of, I mean each of the error terms are m dimensional vectors, and we are having n such errors. So, totally it is n by m Jacobian matrix that we are getting, I mean which is basically the Jacobian matrix composition. Now, we can simply see. So, Jn, the Jacobian matrix, is in fact, tell me, dou E1 with respect to W1, dou W1, then correct, E1 by W2, here E1 by Wm, right. And what will be the second term over here, I mean second row over here, E2 by W1, yes, and here it will be E2 by W2 up to E2 by Wm, and what will be the nth row over here, nth row will be dou En by dou W1, dou En by dou W2 up to dou En dou Wm. So, this is the composition of the Jacobian matrix, okay, n by m Jacobian matrix. All right. Now, using this Jacobian matrix, we have formed this equation. So, ultimately the error expression that we have got is that at the point W is equal to Wn, okay, at the, I mean around this point, the error En that we are going to get is equal to the En plus this Jacobian term, Jacobian multiplied by this weight term, and this has got some significance which I will be coming to very soon. Now, the updated weight vector, okay, the updated weight vector that we are going to have, that is to say that we have, let us say already Wn we have. So, now I am talking of Wn plus 1. Okay. Now, this Wn plus 1 will be what? That will be the argument of minimum over W half of norm E prime in W this square. Okay. This is easily understood. This is to say, this is the error term. E in W is our error term, okay, and we are I mean that is the combined error term, okay, sum total of all the errors, and we are taking the square of that error, okay. So this is actually a vector, isn't it? So we take the squared norm of that vector, and the W, the value of W that minimizes this error term, okay, it is that W that we are going to use as the updated weight. All right, we are minimizing this error, okay, and the corresponding value of W, okay, is the updated weight vector. Okay. Now we again come back to our this equation, okay. From this equation, where the new error vector is expressible as the old error vector plus this term, okay. Here it is possible for us to calculate the error square very easily. You see that if the equation 4 is like this, that is E vector is equal to E n vector plus j n into this, then the transpose of this also will be equal to transpose of the left hand side is also equal to the transpose of the right hand side. Now you just multiply the transpose with the vector, okay. Then what you get? You get the square term, okay. So you can form the square of the left hand side, and then this transpose multiplied by this term will give you a square of this whole term. And what does it lead to? So using this equation 4, in order to evaluate the squared Euclidean norm of this E vector, this is what you will be getting, okay. We will be getting square of E prime n W, okay, that will be equal to half I mean in fact again square term I am deliberately multiplying by half, okay, just so that I mean during derivative I do not have any problem. So half of the squared of En, squared of En square, I mean that is the norm of En square, plus anybody can have a look at this expression and predict the rest of the terms. So this is very clear. This will be squared of this, which will be this plus this transpose into this plus this. So what is it going to be? The first term is definitely going to be E transpose n E transpose, which leads to E n square. This is very clear. And then we will be having two such cross terms where it will be E transpose j n this term, okay. Then there will be another term which will be I mean there will be in fact two such terms. Why? Because this plus this transpose into this plus this, okay. Effectively it is of this form, you know, effectively it is of A plus B transpose into A plus B. That is what we are doing, isn't it? So effectively it is A transpose plus B transpose into A plus B, okay, which will be A square, okay, plus B square term also will come, okay. And what happens is that we will be getting A transpose B plus we will be getting a B transpose A, okay. And in fact in this case what happens is that these two will be, I mean if in I mean this particular case where we are expressing it in this form, we will be getting ultimately this plus the second square term will be, I mean the B transpose part, okay. The B transpose part will be half of W minus Wn, okay, this transpose J transpose, yes, this multiplied by Jn into W minus Wn. Okay, thus second term, simply. Okay. So, there is no doubt about this term, okay. And then the other two terms, okay, they will be equal and they become E transpose n J n W minus W n, okay, this, all right. So, this is the updated weight vector. So, I mean this is the square norm of the equation that we have got. And what I mean, do we need to do now? We need to differentiate this with respect to W. So, differentiate what? Differentiate the left hand side with respect to W means that individually all these terms we will have to differentiate with respect to W. Now, what happens to the first term? First term, if you differentiate with respect to W, 0, because it is not dependent on W over here. Okay. What will be the second term's contribution if you are differentiating with respect to W? In that case, this is with respect to W, okay. So, W J transpose, okay, and you will be getting here, I mean for this, no, this whole thing transpose is there. W minus Wn transpose. So, it is of the form W transpose, I mean it is of the form X transpose W, okay, and there your derivative is simply going to be X. So, in this case the derivative is going to be simply the X term, that is to say by differentiating you will be getting here J transpose n, okay, E n, all right, plus you will be getting another expression, that is this one, okay. This one also will be differentiable with respect to W. Just a minute, we will I mean solve your doubt. Here this is J transpose n into J n, okay, into W minus W n equal to 0 vector, okay. So, this is differentiating with respect to W vector and setting the results to 0 and setting to 0. This is what we will be getting, all right. I mean we will be getting W minus W in this term. So, please verify this expression yourself. In fact, I mean we are already running out of time. So, we will continue from this point in the next class, all right. Thank you very much.